Welcome to solverfy.
Okay, in this problem we have a mass spring system with the total energy given by this expression and a potential energy given by the familiar spring potential. We use the Heisenberg uncertainty principle to say that the product of momentum and position is going to be approximately the h Planck constant. We are asked to find what the minimum total energy is, at what x position we have a minimum energy, and what this ratio of kinetic and potential energy would be at that particular point. So this is going to be a optimization problem essentially, and let's jump into it. So to start us off, we have the equation for total energy, which was shown, p squared over 2m plus 12kx squared. We can use the fact, or the stated assumption rather, that p is approximately h over x. We can plug that in to have E being approximately h squared over 2mx squared plus the familiar 12kx squared. This will be equal to, doing just a little bit of manipulation, we have a constant times x to the negative 2 plus 12kx to the 2. Okay, so we're not going to be able to simplify this anymore. So at this point, to find a minimum energy, we need to take a derivative, set it equal to 0, and find an x that satisfies that condition. This is the usual optimization procedure. So d dx is 0. So we need to take a derivative of this, which we can pretty easily do. We get negative h squared over m x to the negative 3 plus 24kx. These are just doing some power rules, no problem. So now we can multiply both sides by x to the 3, and we have 0 equals negative 8. Oh, this is not an h bar, this is just an h. H squared over m plus 24 kx to the 4th. Let's move over. So thus we have 24kx to the 4th equals h squared over m. You can see where this is going. We get to doing just a couple extra steps. We have x equals h squared over 24km. And it's not a cube root, a fourth root, so 1 over 4. So this is the x value that minimizes the energy, the total energy. So now at this point, we're going to plug this x back into the total energy and see what we can find. So let's rewrite this x just so it's available to us. H squared 24km to the 1/4. So plugging it back into the total energy, we have h squared over 2m. This plugged it with this in 24km. Oof. Squared. Sorry for the bit of latency that's happening. So this is the first term plus 12k x squared. So h squared over 24km. This is to the 1/2. Now let's do as much simplification as we possibly can to these two terms. After a bit of simplification to these terms, we can get a root 6 h times k to the 1/2 over m to the 1/2. Okay, that's the first term, plus 6 over root 6 k to the 1/2 h, or let's put the h out here to make it a little bit more familiar, over m to the 1/2. So at this point, you might see where we're going with this. These are getting increasingly similar to each other. And yes, when we do a little bit more, we're going to end up with something very, very familiar. Okay. Great. So we don't even need to do this. We can, 6 over root 6 is clearly 6 times root 6. Get rid of the square root there. And you can see that these two terms are the same, which is the point. This is the kinetic energy term. This is the total potential energy term. So by plugging in our x for the 0 point energy in to the total energy, we find that k is equal to u. So for the 0 point, when we're at the 0 point energy, the kinetic energy and potential energy are equal to each other. And that's the important result to pull from this. So it took a little bit of algebra, some manipulation, had to be careful, but you should be able to reproduce this result. You should have identical kinetic and potential energy. And that's the main point of this problem.